Hey everyone. In this video, we're going to look at what happens when we try to combine different probabilities together. So first we're going to ask, how much will you make next year? Maggie and Delilah own Hound Sauce Bassett Burgeristas. After much thought, they have finally decided on permanent employee wages, which are randomly assigned using the probability distribution X given below. Additionally, at the end of every year, they give their employees an hourly raise. The bonuses are assigned randomly according to the probability distribution Y given below. And assume that X and Y are both independent events. So out of these two events that we're talking about right here, of letting X be the employee wage and Y being the bonuses and the employee raises, those two events are going to be independent of each other. So we're going to find the mean, the variance, and the standard deviation of the probability distribution X with the hourly wages. So remember, the mean is also known as the expected value. So you could just note this as an E of X. And when we do this, we're taking the outcome and timesing it by the probability of it happening. So we could have a $9 wage, and that's going to be times 0.30, plus a $12 wage times 0.45, and we'd have a $15 wage times 0.25. So we multiply those all, and then we combine all of them together. When we're adding all of those up, we should end up with the expected value of 1185. Now the variance, we needed the expected value to be able to complete that. But in here, we're going to take our value, 9, subtract the expected, square those, and multiply by the probability. Okay, I'm going to do the same thing again. 12, subtract my expected of 1185 squared times the probability of that happening. And finally, we have 15, subtract 1185 squared times the 0.25. Okay, and when I calculate all of that together as we go through, my variance is going to be $4.93. And we know the way we get our standard deviation is just by taking that amount and taking the square root of that. So the square root of my 493, we end up with $2.22 approximately. Okay, so we're always able to kind of calculate our mean and our variance if we have our probability model shown. So again, just as a reminder, this was X, the hourly wages that we've just done this for. We're going to do it all again here, and we're going to do it for the hourly raise, and that's going to be Y in this case. So if you want to take a second, you could pause the video here and just try to do the mean, the variance, and standard deviation just by practicing what we just did. So you could go ahead and do that and pause the video. And when you're ready, just hit play. All right, welcome back. So in this case, as I'm going through, I'm just going to set it up again. We had the $1 raise at 0.70 was the probability, plus my $3 raise, 0.30. And when we go ahead and calculate that, we should get an expected value, a mean of 1.60. My variance, same kind of idea again. We're taking my $1, subtract the expected. We square that times the probability of 0.70 plus $3, subtract my 160 squared times the probability of that. So altogether, when we do that, my variance is going to be a 0.839 roughly. And remember, standard deviation, we just take the square root of that 0.839. And we end up with approximately 92 cents. Like, I'm just going to leave it at 3 digits for now, just to play around with my variation and such. But so now let's go look at what happens when we bring these ideas together. So we want N to represent the new hourly wage for the upcoming year, aka x plus y. So we're taking all the possible values of x and all the possible values of y and putting them together. So remember, x was our wage, so that could have either been 9, 12, or 15. So I'm just going to put that together. We had 9, 12, and 15 here to consider. And then y was the potential raises that were coming up. So we either had $1 or $3 from the previous slide. So when I talk about what are all the possibly new hourly wages, I can combine all these. I'm talking about bringing 9 and 1 together. So 9 plus 1 would be $10, right? I could have 9 and 3, which would get me $12. And we kind of continue this, like we could get $13 as a possibility. We can have $15, $16, or $18. So those are all my possible new wages for the new year, depending on which combination happened. We also want to know, what is the probability of an employee being assigned a $9 wage and a $1 raise. So notice in this case, when we're looking at this here, the most important thing when I'm going to compare these is that it was said that these two events were independent of each other, right? If I go back here, assume X and Y are independent. Since they're independent of each other, the probability of having a $9 wage and a $1 raise would be equivalent to the probability of having that $9 wage times the probability of having that $1 raise. So in this sense, because the two events are independent, we could do a quick 0.7 times a 0.3. I'm getting those values back from over here of the probability of them occurring, right? So 0.9 was my 0.7. Oops, excuse me a second. There's my 0.3 rather. And my 0.7 is my $1. So I just wrote them in the reverse order. So let me just fix that for us. And when I multiply those two ideas together here, I'm going to have 0.21. So that's the probability of both occurring. Again, we knew they were independent. That's why we were able to multiply them. But we're going to fill out that table the same way. So I'm saying that that's my probability of having $10 as my salary next year. I'm going to go borrow everything we just filled out in part A. That's going to be all of our potential outcomes here, right? So I have 12, 13, 15, 16, and 18, all coming from that part A there. And I could keep going with this. I can go get my probabilities of all the other components. If I look here, let's go back. So like for the $12 combination, that was having 9 and 3. So 9 again is 0.3. 3 is 0.3. So this time I'm taking like 0.3 times 0.3 to fill in this table here, which we know is going to be a nice 0.09 for us. We are repeating that process for everything in here. So for the 13, that was a combination of the 12 and 1. So my probability of 12 is 0.45 and 0.7. So we're going to get in here 8.315. And I could keep doing this each time, so just bear with me as I'm kind of just going to fill in our chart here. We get a 0.135. We've got a 0.175. And we have a 0.075. So those are all my probabilities since we had two independent events of each other. So from here, we can do the same thing we did before, and we can go ahead and calculate our mean, our variance, and our standard deviation. So starting off with our mean, same thing again, my expected value, we're going to take the 10 times the probability of it happening at 0.21. 12 times the probability of that happening, 0.09. Now I could write these all out, but since we know what we're doing here, I'm just going to put a nice plus dot, 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 and just kind of skip to that last one, the 18.075. Remember, this is an acceptable notation for the AP exam. If you have more than like 2 or 3 values that you're combining when you're getting the expected value, you can do this. You can do this on our test as well. But in this case, when I go and I actually calculate that whole mean, I'm going to get 13.45. So $13.45. The variance, we do the same thing again as before. We take our value, we subtract that expected value that I just got, the 1345. We square the two and multiply by the probability. I'm going to cheat a little bit here, and I'm going to do the same thing as the previous step, and I'm going to just kind of show my work as me calculating it. 18, subtract that 13.45 squared times our probability of a 0.075. So my variance here is roughly about a $5.76. And remember, our standard deviation comes directly from that. So we take that square root of the 576. So roughly our standard deviation is going to fall at about approximately $2.40, let's say. So I want to kind of see if this checks out for us. So I'm trying to kind of develop a rule here. So we know we took the two together. So we have if n is equal to x plus y, complete the following in terms of x and y. Basically, when I'm looking at this here, this is saying that when I add the means together, what did we end up? So let's go check real quick. So let's go back to the very one. When I did x, we've got ourselves a mean here. And that mean, when we did it, was 11.85. Oops, too far. So for x, we got 11.85. Let's go see what our mean of y was. $1.60. And when we just calculated the mean of both, we got $13.45. Well, in here, if I take my mean of x and my mean of y, we ended up with that 1385 that we did in the previous slide here. Oops, 85. So in this case, this checks out. So the rule for our mean of n is if we can find the mean of both of them separate, we can just add them together as well. So this all checked out when we did it. So because the two added up to that, we ended up with that 13.85 when I found them both. So n is my x plus y. So you can also rewrite this here as the mean of two random variables, x and y, is equal to the mean of each one individually and then add it together. And we're using mu in this case for our mean. Now we want to go ahead and check that same idea with standard deviation. So I'm going to go figure out what my standard deviation was the first time around. So our standard deviation here, we got 222, and we got 0.916. Now, if I go back to my previous slide again, these two ideas are not equal to my 240 that we got in the previous one. So unfortunately, that rule does not check out the same way it just did for us. Instead, when we're looking, we kind of have to think about what this really means. So remember, our variances are squared, added together, and then square rooted. So unfortunately, it's not going to work that same way you think of. When I'm trying to calculate this, I can think about my standard deviation just in general. So if I have the standard deviation of x plus y, we wanted it to equal, to make our rule nice and easy like we saw before, but unfortunately that doesn't check out for us each time. Instead, when I kind of look at this, we're thinking about having x plus y squared, or my standard deviation. Instead, what's happening to us is like we are taking the standard deviation squared and the standard deviation of y squared, and then we're square rooting both of those. So really, if I take those square roots here, the rule for us to get the standard deviation of them added together is to first square them both, add them together, and then square root the entire piece. So that's going to be my rule for these standard deviations. As long as, remember, the big thing here is this works when x and y are independent. Okay, so it will not work the same way if it's not independent. Let's go see what happens on the last piece here. So we've kind of made adjustments and we're going to have some pay cuts going on. So we left the probability the same, but we changed their values here. So instead we were subtracting each time. And so we got our different values up on the top. So we subtracted 9 minus 1. That's what got me my 8. I did my 9 minus 3 and so on for the top. So we kind of subtracted instead of added. So if I were to go and calculate my mean, we'd do the same thing one more time. 8 times 0.21 plus 6 times 0.09. And we kind of go through here and add it through. And so as we go through and kind of calculate that, we could either plug into the calculator, we could do it here. We end up with $10.25. So just to check from before, we had 11.85 and 160. So that does in fact equal the 1025 that we just got. So the mean works the same way for adding or subtracting. The mean of n, in this case x plus y, is equal to the mean of x subtract the mean of y. Okay, so if you're subtracting them, you can calculate the two means first and then go from there. In the variance, I can kind of pull that all out again. But if I do this whole thing, if I do my 8 minus the 1025 squared times 0.21, and I do all of our work out and do it again, my 12 minus 1025 squared times 0.075, we ended up with 576. And the standard deviation then would be about 240, which ended up being exactly what we calculated in the last problem. So if I go back here, I have the 576, the 240. So it got the same value. With standard deviation, we follow the same formula for adding or subtracting random variables. So in this case, it's going to follow the same thing where we have standard deviation of x squared plus the standard deviation of y squared. So that's going to be our 2 there. So again, this only works because they're independent, but since we got the same values in both cases with standard deviation, whether you're adding or subtracting, we'd still do the same formula for both. And we'll look more at that in class. Okay? There is a homework to just try and kind of go with this. So try the questions on that homework sheet that's attached, and good luck. Thanks for watching, guys.